Welcome to my talk. It's about determining the thermal properties of gases under flow conditions. The main reason of doing that is because of flow sensors. We want to know how much of a given gas is flowing through a given tube. But as Jos just mentioned, usually you need at least one calibration point, at least or many calibrations, depending if you change the gas concentration, or if you change the temperature, or any other condition that changes the properties of the gas. So, in this case, I'm dealing with calorimetric flow sensors. Why calorimetric flow sensors? Because they're usually simple to fabricate, they're cheap. And then the way they work is you have a heater that is in, let's say in this case, in the wall of a channel, and then you have two additional temperature sensors that are before and after. As soon as a flow loads up, then the temperature profile shifts, creating a temperature difference between the temperature sensors upstream and downstream. This temperature difference usually depends not only on the flow rate that you have inside the channel, but it also depends on the thermal volumetric heat capacity and the thermal conductivity. So the main focus of this work is to determine those two parameters in order to recalibration processes on the reading that you have on the temperature difference in order to get the flow rate. Basically, we set the scope of this work only for gases. We want to work in a flow range between 10 to 1,000 standard cubic centimeters per minute, with let's say 5% error. So, as I said, usually what we do is to measure the temperature difference between these two sensors, as there is a flow rate inside the channel. And for this, we usually use a single DC excitation. It means the heat generation is always constant, let's say 1 milliwatt every single point. And then we get the temperature distribution inside the channel that goes this way. This temperature distribution, when there is flow, then we have something that's so-called the penetration depth, and it's more or less how much or how deep the heat transfer penetrates into the channel or into the gas that is flowing. What we do is not only, besides of applying a DC excitation, we use an AC excitation. By doing this, we know that the penetration depth is actually affected by the frequency or the oscillation frequency of the excitation that is applied on the heater. So the higher the frequency, the smaller is this penetration depth. By doing this, then most of the heat transfer is actually confined to a region where, assuming laminar flow conditions, the flow rate or the local flow velocity is invariable, small, or close to zero. So in this region, if you confine this to this region, we might think that the heat transfer between, let's say, a heater here at the middle and another temperature sensor right between the heater will be independent of the flow rate. And if it's independent of the flow rate, then it should be only dependent on thermal properties of the gas that is flowing there. So the way to assess how those thermal properties are is by measuring the amplitude of the temperature oscillations and the phase shift between those oscillations and the sinusoidal signal that is being applied on the heater. So this way, if we are able to determine thermal conductivity and the heat volumetric capacity, it should be possible to determine the flow rate without doing an extra calibration. So the sensor we're using is was meant originally for a two-dimensional flow measurement. That's why if we closer look at the membrane that is at the center of the chip, we'll find 4 concentrical thermistors to measure the temperature oscillations. But what is important is that we have this central pair, which is made up by a germanium thermistor, which has a quite high temperature coefficient of resistivity, and a chromium heater that is closely surrounding it. So the idea was to then determine how this pair will behave by different gases. So for this, we came up with this simple analytical model, which is actually a it's called prolongation of a model that was actually also proposed by Roman. Here we have three different sections. On the top we have gas that is moving, then we have the membrane, just considering the central thermistor and the heater is around it. And just below we have the same gas to increase the sensitivity to the thermal properties of that gas. So we start with the heat transfer equation, which includes a diffusion term, a capacity term, and also a convective term. But as I said, by increasing the frequency to a certain value, we could get rid of the effect of the velocity. That's why then we get rid of this term. Now, for easing up the analytical modeling, since I'm working in the frequency domain, then apply the Fourier transform to this equation. And the signals that I'm interested are then this amplitude measure of the, this amplitude measured at the central thermistor, and the phase shift between this temperature measured and the input heat signal. This differential equation is still a partial differential equation, meaning that I have two dimensions to consider. So in order to make it even more simpler, I apply again a Fourier transform, this time in space domain along the x-axis, which reduce. I mean, I can do this because of the nice symmetry I have along the y-axis. By doing this, then I just get an ordinary differential equation, which is second order, and this can be easily solved. And the temperature then at any point in this boundary will then given by this by the general solution. The constants will then given by this, and in order to recover the actual temperature at the thermistor, I need to apply the inverse Fourier transformation in space, which in this case, given the complexity of the function, is done numerically. So now let's look at the results. So what I want to see here is how then the amplitude and the phase shift measured at the central thermistor will depend on the thermal properties of gases. That's why then we have the thermal conductivity, typical thermal conductivity for gases, and the typical volumetric heat capacity for gases. In this case, I'm considering this product, which is the density times just the heat capacity. So on the left side, we get the amplitude. What we first see, and also on the right side, we get the phase. What we first see is that most of the lines are actually either completely horizontal, or like in the red side, or the slope is quite small. That means that most of the dependency is actually on the thermal conductivity, meaning that we have a weak dependency on the heat capacity. Why is this? Because although we have a really thin membrane, the volumetric heat capacity, I mean the product of density and heat capacity of the membrane, is way larger than than that of the gases. So the sensitivity is actually quite reduced. Still, we can see that it could be possible to determine it. What is important to see here is that given that these lines are totally horizontal, it would be possible to determine from the phase the thermal conductivity directly. I mean, for instance, for let's say this is the case of air. This is the volumetric heat capacity for air. We see that the relationship between the phase and the thermal conductivity can be fitted quite nicely by this equation. So for this equation, then these constants A, B, C will be just sensor dependent. I mean, will be requiring just a single calibration step, and then we'll be good to go to determine any thermal conductivity. So how can then I determine the heat? I mean the volumetric heat capacity. So let's say we have a gas that is flowing. We have a measurement of 5.2 kelvins in the amplitude and 85 degrees in the phase, and let's say I have achieved a 1% error on this measure. So directly from the phase shift, I can determine the thermal conductivity But in order to determine the volumetric heat capacity, then I can look the point where this horizontal line crosses with the amplitude that I have measured, mean 5.2. The green lines around it are this 1% error around the measurement. So from this point, I could say, okay, I can determine the volumetric capacity, which in this case will be 1.92. But the problem is, given that the slope of these lines is quite small, then the error that I have associated is quite large. In this case, it's 30%. So that brings us to say, okay, if I need a 5% error on the output, how much accuracy do I need in the initial measurement? So for the phase, it's not that much. I mean, 1% is quite enough. But for the amplitude, I will need a 0.1%, which is, well, quite small. So just to verify, at least, whether what I got here is true, we have a small experimental setup, which just considers, as I said, sensor, the one I showed you before, where I have laminar flow with stable flow profile, flow on top of the membrane, and then the gas just in stable position in the underside. So here, first, we see that both the amplitude and the phase shift remain stable for a flow rate from 0 to 1,000 milliliters per minute. Actually, the small percentage is on, the largest variation is just for helium and amplitude and phase. Moving forward, because I'm running out of time, this is the comparison between the model that I have, which is what I got from an analytical model, which is here in analytical, and experiments. The curve that you see here is the fit using this curve for all the experiments. At least 19 gases and different composition of those gases. Even for this small region, we have a really good agreement. And what we can see is that it's a really simple analytical model. It's just one-dimensional or two-dimensional. We can predict how the sensor is going to work, although we still need to work on how to determine the volumetric heat capacity. About at least theoretically, it can be done. And we're already working on ideas on this. Thank you very much.